It's like everyone in the middle would sit in every other.
Okay, let's go ahead and get started.
He's so awesome. I want to go back like every month. Let's go. Some crazy things too. I've done when I
Ebarua.
wanted me to go. It's like there's so much we did. Move my stuff.
We finally have gotten to the good stuff where we can talk about things that are more exciting than just the basics. Would someone be willing to give us an opening prayer to get us started today? Thank you very much.
Our dear Heavenly Father, we're very grateful for this opportunity we have to be here, gathered together as a student body to come and learn about Thy world and the universe which Thou hast created, and physics, and that we have an opportunity to learn from a great professor. We ask Thee for his health. Please bless him with health and safety. And we pray for all the students who aren't here or who are on their way, that they can be safe in getting here. And we pray for these things and thank Thee for Thy Son, Jesus Christ, and for the atonement. And we pray for these things in the name of Jesus Christ. Amen.
Amen.
It's good. It's
Okay. We're gonna race through three concepts today, and the first one is the Doppler shift, and you have all experienced the Doppler shift, and in everyday life. So even if you were at that racetrack with your eyes closed, you would know when the cars were coming towards you and when they were going away from you and when they passed you. Okay, and that's the Doppler shift that we'll talk about today. But before we do that, I want to give you some help on your tutorial homework. Make sure that we are all comfortable with that. In the tutorial, we built a model for the reflection of a pulse when it reaches a fixed end. When it comes down a wire or a string or a spring, and it hits a point where it's tied to the wall. And what we found was that it came in and it collapsed, and then it came out on the bottom. And we saw an example of that in our last lecture. Now, again, with fancy mathematics, a differential equation, we can actually predict what it's going to look like as it comes in and collapses and inverts. But we don't need to. We found in that tutorial that there was a much easier way that gave us the same answer, and all we had to do was simple addition. Okay, we didn't have to do any fancy mathematics. What we did is we pretended that that wire or spring or string, whichever it was, didn't end at the wall. That it went behind the wall where the spiders live, where it's dark. Okay? And that behind the wall, there was a second pulse coming the other way towards that wall. And that second pulse had to have a very special shape, and it had to be in a very special position. And you remember, the special was that it had to be the original pulse reflected across the boundary and inverted. Okay? It's got to reflect it across the boundary and then invert it. And if we do that, this point right here that's halfway between the incident pulse, the original pulse, and the reflected pulse, that point halfway between them won't move. Whether it doesn't move because it's tied to the wall, or whether it doesn't move because of these two pulses interfering with each other, don't matter. Either way, it doesn't move. And so we get the same physics. Okay? So when this peak here reaches the wall, so does this negative peak, and they cancel out. When this point here that's halfway up reaches the wall, so does this point here, and they cancel out. The symmetry is what causes the cancellation at every point in time. Now, what we can do with this is essentially solve the difficult mathematical problem just by adding. If I let this original pulse move to the right by 2 squares so that it's there, you see it moved 1, 2 squares, well, the reflected pulse is on the same spring with the same mass density and the same tension, so it's got to move the same speed. So it's got to move 2 squares to the left. And now I just use superposition, which is a fancy way of saying add them up. Okay? Here I've got a plus 3/4 on the incident pulse. I've got a minus 3/4 on the reflected pulse, and that adds up to 0. Here I've got a 1.5 on the incident pulse and 0 on the reflected. Well, that's 1.5. And here I've just got the incident pulse. And so that's what the pulse looks like after it's moved 2 squares to the right. Well, now let's move it 4 squares to the right. And again, the reflected one's going to move 4 squares to the left. And now I add them up. And folks, I don't care what happens back here where the spiders live. That's just make-believe back there, okay? I just care what's going on in the daylight, okay? And so here I've got 2 1/4 on the incident, negative 2 1/4 on the reflected. That gives me 0. And then here I've got 3 on the incident, negative 1.5, and so that gives me 1.5. Here I've got 1.5 and negative 3/4, give me 3/4, and then 0 and 0. So that's what the spring would look like when the incident has moved 4 squares to the right. Then I move it 6 squares to the right, and you see I've just got the tail end of the incident pulse here, and likewise I've just got the tail end back behind the wall of the reflected pulse. Well, I add them up. I've got 1.5 here, and I've got negative 1.5, that's 0. And then now I've just got the reflected pulse. And so now it looks like the reflected pulse, except for the tail end's been kind of carved off. And now if I wait till it goes 8 squares to the right, and the reflected goes 8 squares to the left, now you see the reflected pulse is in the daylight all by its onesies, and what we get is just the reflected pulse.
I guess my question is, sorry. So are we supposed to calculate it one by one, like one column by one column?
Yes.
Okay. Yeah.
Yep. And that's just for convenience. I put the grids in there just so that you can, know what to add. Okay, so what we just saw was that original pulse came in, and the front of it buckled. Oh, okay. The front of it buckled a little bit, and then it crumpled to where it was almost gone, and then it came out on bottom, missing the tail end, and then it was whole again. That's messy. That's complicated. And yet all we had to do was add it up. Add it up. It was that simple. It was that simple. Now, it's important to note that when a wave or a pulse runs into a boundary, it doesn't turn around the way normal physical things do, okay? It turns around like a snake in such a way that the leading edge stays the leading edge. By leading edge, I mean the part of this pulse that's leading the charge. This thing's going to the right, and that's in front, okay? And I'm going to color it blue. And when this thing bounces off, what I saw was it was the same part of the pulse that was leading the charge, same leading edge. And this is not the way physical things in our world bounce off of walls. If I had a ball that was blue on one side and the red on the other side, it's going in with the blue side leading the charge. But it bounces off with the red side leading the charge. And that's because the ball all bounces together. As soon as it hits the wall, it all bounces together. Not so for a wave. For a wave, the front of it bounces and turns around, while the back of it is still moving towards the wall, like a snake. See if your neighbor understands what I'm talking about when I talk about snakes. Okay. Now, right at the end of that tutorial, you saw a video of a pulse arriving at a free end. And a free end we create by having a massless ring attached to a frictionless rod. And you know that there's no such thing as a massless ring and there's no such thing as a frictionless rod. But if I have a light ring and a pretty slippery rod, I can get a pretty close approximation to this free end. And what we saw was that when it came in, it didn't invert. Instead, I got when it reached the boundary, it went twice as high as the original pulse. And then it came back, it reflected on the same side, not the opposite side. Now, you've probably experienced this the last time you were in Cancun, okay? And you're sitting there at that fancy restaurant and watching the waves come in, and there's a seawall there. And when the wave comes in and hits the seawall, it splashes up twice as high as the level of the wave, okay? And then goes back out. Now, I, again, have this cartoon in my head of what a pulse is. And remember, it was those football players. And one of them jumps up, pulling his neighbor, who pulls his neighbor, who pulls his neighbor, who pulls his neighbor, who pulls his neighbor. And then we get to Fred, and instead of being attached to the wall like we were with the fixed end, he's not attached to anything. So he's ready to pull on his neighbor, and there's nothing there. And so, whoa! And then that sends the pulse back the other way. It's kind of like when you're pulling on your shoes, your shoelaces to tie them, and you're trying to get them really tight, and then they break. Okay? See if your neighbor is understanding my cartoon.
So, your shoe.
Like instead of
There's, and then there's, oh, and then there's,
it'll put it pulls back down. Is the stopping it? It's just
I'll get that.
and then it'll just.
Why is the reflection, why is the amplitude doubled? First of all, how do we model this without fancy mathematics? Well, I want something coming in on one side and reflecting off on the same side, and I want the leading edge to stay the leading edge, because that's what I see in real life, okay? And so what I do is, again, pretend that there's no boundary and that this wire or spring or string continues on forever. And then I pretend that there's a second imaginary pulse coming the other way. And this pulse is reflected across the boundary, but I don't invert it. I just reflect it, okay? And when these two come together, you can see that when this point here reaches the boundary, this point here will have reached the boundary, and they add together. Since this one was 3 squares high and this one was 3 squares high, I would have 6 squares high. Okay? Now, the demonstration that you saw was a version of this, where I've got a free end. Lucas is holding this rod. He's got his finger between the rod and the floor so that the ring is free to slide along that rod. And we've got cups set up, but they're further away from the spring. And this is an old video. These turned out to be, it's an old building. They were all asbestos. We were all getting poisoned, and then they ripped them out so that we could breathe the asbestos while they were ripping it out. So it's all good. Okay? And so watch this pulse come in. The pulse is smaller than the distance to those cups, but I still knock out that cup that's right by the boundary, because right there, the amplitude's going to be twice as big as the original amplitude. Okay? Now, the hardest part of that tutorial homework is the section on the boundary condition and why the boundary condition has to be 90 degrees for a free end. And that's what everyone gets tripped up on. So let me see if I can help with that. For a truly free end, we've got 2 criteria. 1, the rod has to be frictionless. 2, the ring has to be massless. And those 2 conditions, combined with Newton's second law, force us to this boundary condition. Let me explain. If I try to make that angle that the spring, string, or wire makes with the boundary, if I try to make it something different than 90 degrees, it will instantly change itself to 90 degrees, faster than you can think, faster than AI can think, okay? And if I try to change it somewhere else, a different angle, pow, faster than you can ever think. And it will always be 90 degrees, always. Now, why? Why? That's part of the homework. Well, first of all, let's do a free body diagram for that ring or pulley or whatever you're using for your free end. My first condition was that this rod has to be frictionless. Well, if there's no friction on the rod, the only force that rod can put on that ring or pulley is a normal force, right? Those are the only 2 flavors of a push that's contact, normal or friction. If there's no friction, what's left? The normal. Now, the second condition for a free end was that the ring or pulley had to be massless. Well, think about F net equals ma. If m is equal to 0, we don't care what the acceleration is. We don't care what a is. You multiply it by 0, you get 0. That means my free body diagram has to scream balance. And I've only got one more force in my quiver to put on that diagram. And that's the tension force by the spring, string, or wire on that ring. Okay? And so if this one is perpendicular to the rod, by definition, it's a normal force. This one has to be perpendicular to the rod. Talk to your neighbor. See if your neighbor's understanding that boundary condition.
I'm still catching up, but I'll get there.
An application. Yeah, it's fine. There's thought. Like I cannot.
I'm looking for the force on the pulley. And since it's pulling, you can see that the spring's pulling to the left, right? So the rod has to be pushing to the right. Yeah, it's riding on the side. Okay, question. Are we assuming a mathless string? It turns out that, and I apologize for this, but what we assume is that the mass of the string or spring is very, very small compared to any blocks that are hanging from them. But you remember that the speed of the pulse depends on that mass density. And indeed, it was the square root of the tension divided by the mass density. And so if we go all the way to a massless spring or a massless string, we're dividing by 0, and that makes your calculator blow up. There's shrapnel all over the room. It's nasty. So we just assume it's small. Okay, thank you for that question, Thomas.
So, Professor, why theoretically could we not have a tension coming?
Why is what?
Why theoretically could we not have a tension coming in at an angle and normal force at an angle? Is it because normal force has to be perpendicular?
Yeah, because normal means perpendicular, and it has to be perpendicular. And so now, the very next problem in your homework, after you establish this boundary condition, I'm sorry, is there another question? Yes, sir.
Oh, I was just going to ask, how, if there's only perpendicular forces acting on it, how does it move up and down?
How does it move up and down? That's the thing we learned in that tutorial in 105 with when we were talking about tension. And that is F net equals ma. If m is 0, I can have any acceleration I want without any net force. Okay. There's nothing to push on. Okay. Right after we establish this boundary condition, we're faced with a conundrum in the homework. And that is, you're given an asymmetric pulse that has a nice sharp peak on it, and you're asked to figure out what the pulse of what the shape of the spring looks like as it runs into this free end. And what you find is that it doesn't come into the boundary at 90 degrees. It violates this boundary condition. It violates Newton's second law. And we know that that's just not possible. That causes the end of the universe. Cats and dogs living together. Anyway, what that tells us is that these idealized pulses with the sharp peaks on them aren't physical, aren't something that can exist in nature. We use them because they're easy to work with mathematically. They're easy to do the superposition with. But in truth, when you saw those pulses going across the floor, they were rounded. They weren't sharp peaks in them. Okay, and that was the takeaway from that homework problem, was that those can't exist.
in that case, would the tension just be the cosine of whatever angle it's making the impact? In that case, would the tension just be the cosine of whatever is making the?
I can't hear it.
In that case, would the tension be the cosine?
Oh, the tension is not something we're ever going to be looking for. It's just the direction, and so try not to read too much into these homework problems. Like the last homework problem on the tutorial homework, I know a lot of people worry a whole lot about. You're just looking at a bunch of examples of fixed ends and free ends, and in the fixed end case, sometimes they don't stay fixed. In the free end case, sometimes they don't come in at 90 degrees. It's no deeper than that. It's no deeper than that. Okay, let's talk about the Doppler shift. That's what sirens sound like in Europe. And again, you hear that high-pitched frequency and then that low-pitched frequency. I love this cartoon. I love hearing the lonesome wail of the train whistle as the frequency of the wave changes due to the Doppler effect. That's what they're saying there. Why don't we rob that train, Luke? Okay. When I was taught the Doppler shift, I was taught through equations, through mathematics, through very messy mathematics. And that's the way I understood it. And that's the way I taught it for a long time. And then I got married to my dear wife, and shortly after we were married, I was at her house when her teenage sister came home with some of her friends. And they were learning about the Doppler shift in their high school class and weren't understanding. And so my sister-in-law, Laurie, says, Greg's a geek. He can explain it to us. So I sat down at the table with these three young ladies and tried to explain through equations the Doppler shift. And they weren't getting it. They were getting more and more frustrated. And I could tell that this was about to blow up. And so finally I just said, ladies, let's go to the bathroom. And so we got up and we walked down the hall to the bathroom. I filled up the tub and we knelt down in front of the tub and I started tapping on the water. And that's the way I taught them the Doppler shift. And that's the way I'm going to teach you. So if we could all stand up and go down to the bathroom. Okay, we're going to use our imagination. We're going to use our imagination, and we're going to imagine that we're looking down on a pond, and in the middle of that pond is a skeeter bug. His name is Bob. And Bob likes him some music, not really music, country and western. And Bob likes to stomp to the music, stomp to the music, stomp to the music. And every time he stomps, he sends out a pulse, a ripple of water that goes across the pond in all directions. And he stomps and he stomps and he stomps. Now, if I were to put a little leaf right there, or indeed a leaf right there, or there, or there, no matter where I put the leaf, it would bounce up and down with exactly the same frequency that Bob was stomping, okay? Because he's creating those ripples, and they're taking off, and they're all going the same speed, so they're going to get to that leaf at the same timing as he's making them. Does that make sense to everyone? Okay, good. Now, Bob has a brother. His name is Billy Bob. And Billy Bob, he likes to move, okay? And so he doesn't just stomp. He stomps and slides, stomps and slides, stomps and slides. And every time he stomps, he just keeps sliding. And so the ripples, think of these as little hills of water on the above the surface of the pond, okay? And so this one here is the first one that he created when he was at this location and stomped. This dotted line here is the ripple that he made when he was here, and it's, you can see in the center of that circle. And then this one here is the one that he made when he stomped there. And when he's here, he hasn't stomped yet. He's about to stomp. Now you can see that because he's been moving into the ripples on this side and moving away from the ripples on that side, the ripples got bunched up over here, and they got spread out over here. So if I put a leaf over here, it's going to go up and down. It's going to oscillate at a higher frequency than what he was stomping at. And if I put a leaf over here, it's going to go up and down at a lower frequency. Now, we're not really interested in leaves on a pond or skeeter bugs. We're interested in sound waves due to some source of sound, some engine that's making noise or some siren that's making noise. And so if I put my detector here, instead of a leaf, I put my ear, then I know that the wavelength is from crest to crest, from ripple to ripple, okay? With sound, that would be a compression to another compression, okay? And I know that that wavelength has been made smaller by this bunching. Now, if I look at the wave equation, the speed of sound is still 343 meters per second. That doesn't change just because Billy Bob's moving. If the lambda, if the wavelength gets smaller, the frequency has to get larger, has to increase, okay? On the other hand, back here, the wavelength got bigger. The speed is still 343 meters per second. If the wavelength got bigger, the frequency has to get smaller. And that's what you are hearing. Now, I can demonstrate that with, someone's probably going to get hurt here. I apologize. I've just got a source of sound in here, a pure sine wave, and we'll see. Did it sound different when it was coming towards you than away? Yeah. Okay. Back at Montana State, I had a speaker on a long stick, and I would make it go towards you and away, and towards you and away. I bless you. I bless you. And I could get away with that because Pope Francis was my uncle. Not really. He's Catholic. Actually, he's dead. So, but back then he was alive. Now, when I say someone's dead, you're not supposed to laugh. That's just bad taste. Okay. Okay. Now, I've got another example of that. I've got a source inside this Nerf ball. Now, be awake and catch. Throw it on back. Okay, as it's coming towards you.
It's out.
It's off? Oh, I don't know. Okay. Oh, yeah, we broke it. Okay. Oh. That's going to come out of my salary. Okay, never mind. Leave that one right there. Okay. So this picture comes out of Paul Hewitt's book for the conceptual physics class, and I show it to you I also have a conceptual physics class. It's not the one you're using. Conceptual physics textbook, not the one you're using. But my textbook is the second best-selling textbook for that particular class in the United States. And that's what I told my father when he was alive. What I didn't tell him was that I only had 2% of the market share, and Paul Hewitt had 98% of the market share because he could draw really fancy cartoons. And I think he owns his own island. But with that book, I made something like $2.50 an hour working on it. But this is supposed to give you that image of the wavefronts being bunched up in the direction of motion. So let's see if we understand this. A stationary source of sound, like a whistle, produces waves, and you measure their speed, wavelength, and period, also the frequency. If the same source is moving towards you, and you make the same measurements, what changes and how? So shout out the answer. Speed, does it go faster, slower, or the same? Speed of the wave. Same, okay. What about the wavelength? Shorter, okay. What about the period? Shorter. Yeah, remember those two trains coming towards you, okay? And that means the frequency is going to be higher, okay? Yes, sir.
Does the wavelength of wave that's traveling towards you...
Is the wavelength...
Yeah, does the wavelength differential depending on does it depend on the velocity of the sources?
Well, the wavelength is just from crest to crest. And once that's determined, if the speed is 343 meters per second, that determines the frequency. Okay, it's not the in this case it's not the wavelength that determines the speed; it's the speed that determines the frequency. Okay, now if that same source is moving away from you, well, the speed of sound doesn't change. It's still 343 meters per second. But now the wavelength, the distance from crest to crest, from compression to compression, is longer. So the period is longer, and the frequency is lower. Okay? Now I'm going to demonstrate this once again for you. And, listen carefully. No mercy clapping, no mercy clapping. The point I'm trying to make is that this shift only happens when your speed is some appreciable fraction of the speed of sound, okay? And there's no way we can get this old man moving anywhere close to the speed of sound, which is 700 miles per hour. So, well, there is one way. The Doppler effect. Okay. So, question. What would this sound like as you've got a whistle that's always blowing at a constant frequency, let's call it 400 hertz, and you're running towards it at a constant speed, okay? Is it going to sound, there are two things we need to keep straight. Volume, the loudness, is determined by the amplitude of the wave. The pitch, the frequency, whether it's high or low, that's the frequency of the wave. And so my question is, as I go towards this whistle, Do I hear something that's higher and higher and higher, or just higher? Talk to your neighbor. Which is it going to be?
Towards the whistle is
Okay. It turns out, and again, we're not going to go through the mathematics, but it turns out that this shift is going to be determined by the relative velocity of the observer and the source, okay? And so as long as you're going at the same speed, call it 30 miles an hour, towards that source, you're always going to hear the same shift. Because you're going towards the whistle, you're going to hear something higher than 400 hertz, maybe 408 hertz. But you're going to hear 408 hertz, 408 hertz, 408 hertz, 408 hertz. As you get closer and closer, the volume's going to get louder and louder. But the frequency is going to stay 408. Okay?
until you stop, right?
What's that?
Until you stop.
Until I stop, and then it's going to be 400. Yeah. And so this is just while I'm going at constant speed. Just while I'm going at constant speed.
Accelerating with the frequency station?
Oh, that's the homework. Yeah. Yeah. That's a good question. It depends on whether you are going towards or away from something. If I'm going towards something and the frequency is above and I am speeding up, the shift's going to get bigger, and so it'll go up. But if something's going away from me, so I'm hearing a shift below, then that shift's going to get bigger as I speed up, which means it's going to get lower and lower or further away from the 400 hertz.
So, I don't know if that's what he was asking, but
What's that?
what will happen if you have a positive velocity towards the sound source but has a negative acceleration? Slowing down as you're running the direction towards the sound.
So, are you going towards it or away from it?
Towards the source, but slowing down.
Slowing down means the shift is going to get less and less, which means it's going to go closer and closer to 400, so it'll be going down. Yeah. Okay, this is an old exam question. You've got a child on a swing, and we're just going to look at the part of the swing from A to E. And there's, again, a whistle that's blowing at a constant frequency, again, 400 hertz. And we want to know at which position will the child hear the highest frequency for the sound of that whistle. I'm going to get you started here. Okay, now you can click.
So,
It could be something weird about
Okay, last call. Get your vote in. Okay. think that's all of us. Okay, you said a point C, and that's the correct answer. You remember from Physics 105, you're speeding up from A to C, you're slowing down from C to E. You're going the very fastest, the child's going the very fastest at point C. And this shift is dependent on the speed. And so it would be, the bigger shift would be at C. At E, you got to stop to turn around, and so at E, the child would be hearing 400 hertz, the frequency of the whistle. Okay, so the answer is B. So the key concept is that louder is a very different concept than higher. Middle C on a piano moving at constant speed does not sound higher and higher as it gets closer and closer. If you had a piano on wheels and you were just running it down the road at 30 miles an hour and hitting middle C, what people in front would hear would be something higher than C, maybe D, but it would just still be D, 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 louder and louder, but it'd still be D. Okay? Well, let's change topics and talk now about Mach cones. And to do that, we're going to go back to that pond, and we're going to look at another brother of Bob's. This is Billy Joe Bob. And Billy Joe Bob, he's really fast. And he stomps and slides and stomps and slides and stomps and slides and stomps and slides and stomps and slides. Now, if you think of these circles as little ripples, little hills of water that are each, say, 1 millimeter high, first of all, you notice how fast is Billy Joe Bob compared to the speed of the ripples?
Same.
Almost the same speed. Just a little tiny bit slower, okay? And just almost the same. And so what you see is that right in front of Billy Joe Bob, he's got a mountain of water. You know, if we don't take into account nonlinear effects like surface tension, all of these things would add up with superposition, and he'd have a mountain of water in front of him that he'd have to get through. Now, we're not really interested in skeeter bugs. We're interested in fighter planes, okay? And as they get going very close to the speed of sound, all of this compression that they've caused with their engine by sending out noise is all right in front of them. They've kept up with it, and it's all superimposed. So that's what we call this the sound barrier. I was losing my words, okay? It's going to happen to you someday. Just be patient with me, okay? The sound barrier. I used to think that that was a psychological thing, like the 4-minute mile. When I was young, no one had ever run a 4-minute mile, and we thought, oh, no one can do that. Well, that was just some psychological thing. But this is a real barrier. This is a lot of compression that, as you, did anyone see the movie The Right Stuff? Okay, they're trying to break through the sound barrier, and their plane is just, you know, rattling apart. It's like my car going down the road. And that's because they have to punch through all of this sound that's bunched up there, okay? Now, if we go even faster, you see that here, that's how far Billy Joe Bob's gone, and the ripple's only gone that far. So he's going faster than the speed of the sound, okay? Now, when something's going faster than sound, what happens is that we get these circles bunched up. Now, I've only drawn circles for a constant stomp at one frequency. but engines make white noise, which is all the frequencies, all the noise. And so I would have an infinite number of these circles, and they would all overlap along these two lines. But these are only lines because I'm drawing this on a two-dimensional screen. In 3 dimensions, what are these going to look like? Like a cone, like a cone. And we call that a Mach cone, a Mach cone, after Ernst Mach, a German scientist. Question?
Is the cone made from water? Like water being compressed from the air and so it condenses and stuff? Or
Ask that again, please.
is the cone water? Is it literally water molecules that are gaseous?
Oh,
being
no.
condensed?
It is actually air that's compressed, but when there's humidity in the air, that can create clouds that we can visualize the Mach cone with. But it's actually the air that's being compressed with the sound. And, well, I guess the humidity's in the air. It's whatever's carrying the sound. Yeah. Now, let's figure out what this Mach cone looks like. First off, what we want to do is set up a right triangle where the hypotenuse here is how far the plane has traveled while we were watching, okay? And this side of the triangle is how far the sound has traveled since we started watching. We started watching when the plane was there, and the sound made it out to here, okay? Now we define this angle, we call it the Mach cone angle. Actually, it's the Mach cone half angle. And let's think about what that Mach cone angle tells us. If I had 2 planes, that one was going Mach 2 and one was going Mach 5, well, first of all, what does that even mean? A plane that's going Mach 2, tell your neighbor, what does that mean? Mach 2.
That's what I was thinking.
Okay. Mach 2 just means twice the speed of sound. The speed of sound is 343 meters per second, so you're going 686 meters per second. Mach 5 is 5 times the speed of sound. Okay? Which of those planes is going to have a fatter Mach cone? The fast one or the slow one? The slow one, yeah. The faster you're going, the smaller that angle is going to be. And indeed, we can find a relationship between that angle and how fast the plane is going. If I can measure that angle of the Mach cone, I can tell you exactly how fast that plane is going. Now, we're going to do just a little bit of trigonometry, not much. The hypotenuse here of this right triangle, that's how fast the plane is going times the number of seconds that I was watching. That's just how far the plane went while I was watching. This side, the opposite side from the angle, is how far the sound went in the time that I was watching. Everyone see that? Now I know that the sine of this angle is equal to the opposite side divided by the hypotenuse. Well, that's going to be equal to the velocity of the sound times time divided by the velocity of the plane times time, and the time cancels out. And so that's going to give me 1 over the Mach number. If the speed of the plane divided by the speed of sound is the Mach number, then the speed of sound divided by the speed of the plane is 1 over the Mach number. Check on your neighbor real quick. See if your neighbor's there.
I didn't catch the last part, but I don't know. Yeah, sort of have to be.
Then that gets you.
This is the triangle you should be looking at. This is the hypotenuse. This is the opposite side, opposite for this angle. Okay. A word of warning. There will be at least one, probably two, Mach cone problems on the next exam. And if you solve those problems without using that equation right there, you're not getting it right, okay? You're getting 0 points, okay? Because that's the key to solving these problems. And I'll show you an example in just a moment. Now, as was just mentioned, sometimes we can visualize these Mach cones because moisture in the air we have a phase change that creates a cloud. Let me demonstrate that for you. I've got a bottle here, and I'm just going to put a little bit of alcohol in here. I got permission from the university. Actually, it's isopropyl, so it's okay. If I increase the pressure in here and then decrease it, I create a cloud. Okay. I need more alcohol. Got a problem. Now what's going on there? I don't know if you've ever done this, but if you take a fire extinguisher and you spray it, what you're doing is you are releasing the gas. You are expanding the gas. And when a gas expands, it cools. It becomes a lower temperature. And the bottom of that fire extinguisher is going to frost over. Okay? Many years ago, 30 years ago, when my daughter turned 16, her friends talked me into climbing into a professional clown outfit and meeting her at the front steps of her high school with 16 balloons and 16 roses and floppy feet and a big old red nose. And I brought a fire extinguisher just for fun. And I followed her all the way to her German class, yelling, "It's Heidi's birthday! I'm her boyfriend!" And I would spray all the students along the way with the fire extinguisher. And she was mortified. She was so humiliated. And then I got into her German class, and I accidentally hit Frau Schmidt in the legs with the... I regret it now. But Bozeman High School has been a clown-free zone for 30 years. I am responsible for that. So an expanding gas is going to cause that temperature to drop, and that can cause a phase shift like we saw here. Now, if we look at that sonic boom, has anyone heard a sonic boom? Okay, yeah, and what you hear is actually a sonic ba-boom, and that's because the front of that bow wave is a high pressure region where the compressions are bunched up, and then behind that there's an eddy, kind of like behind a rock in a stream, where there's the low pressure that's bunched up, and so the front of that ba-boom is your eardrum being pushed in, and the back is your eardrum being pulled out. Ba-boom. Now, when I was 16, 17, I was living on Guam during the Vietnam War, and we lived just down the road from Andersen Air Force Base, and every 30 minutes during the end of that war, B-52s were taking off to go bomb Vietnam. and there were fighter jets coming in all the time and leaving, and we had sonic booms all the time. And I thought, I had a misconception. As a teenager, I thought that you only got that boom when the plane went through the sound barrier, that crashing through the sound barrier caused the boom. But in truth, once the plane is going faster than the speed of sound, it carries this Mach cone with it wherever it goes. I was the luckiest kid on the island when it went past my house, but then the kid down the street was the luckiest kid, and the kid down in Dadido was the luckiest kid when it finally got to his village. And so it just drags along as you go. And here's some footage now. This is a Navy ship, and this is a plane that's being tested, and it just comes past the ship in a region where there's some moisture. So I could give you that picture in a protractor, and you could measure that angle, and then you could figure out how fast that plane was going as it went through. And here's some other pictures. You notice that those cloud representations of the Mach cone are right where the turbulence is the greatest, near the engines and near the cockpit. That one's a messy one, but that one's nice and clean. And just to point out that there are other ways that you can get these cloud formations. We're pretty sure that plane is not going faster than the speed of sound. Okay, so this is the type of problem that you would have on your exam. You look directly overhead and you see a plane exactly 1 kilometer above the ground, traveling at Mach 2. How far will the plane travel before you hear the sonic boom? Well, it's 1 kilometer above you. It's got this sonic boom dragging behind it, and you hear it when it's some distance x past you, and you're on level ground, okay? And so this becomes a trig problem. First of all, I need that angle, and I find that angle from this formula, the Mach cone formula. I know that the sine of that angle is 1 over the Mach number, and we're told that the plane's going Mach 2. So that's sine is 1/2. And so I plug into my calculator, the inverse sine of 1/2 is exactly 30 degrees. So that Mach cone angle is 30 degrees. Now I just use trig. I know that the tangent of 30 degrees is equal to the opposite side, which I know, divided by the adjacent side, which I'm looking for. When I do the math, I get 1.7 kilometers. Now, again, be careful. You're going to be tempted to say, well, Greg, if sound can go 1 kilometer to your ear, and the plane's going twice as fast in that direction, wouldn't it go 2 kilometers in the same amount of time? But that's not the answer. The answer is 1.7. And the reason is, when you hear the ba-boom, it's not sound coming from the plane when it's directly above you. It's sound coming from the plane back here in a direction perpendicular to the Mach cone. Okay? That's why the simple answer is the wrong answer. If you're not using that formula, just give yourself a 0. Check on your neighbor quick.
I don't understand that.
Okay.
I'm so tired.
We've got one more idea. I've got a speaker there. Turn it down, Greg. That's 500 hertz. This is 504 hertz. This is both of them. You hear the wah-wahs? Wah, 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 wah. Now, if I make this 505, you get more wah-wahs. If I make that 503 and 500, I get... If I make this 510, okay. Now, I can also demonstrate that with these tuning forks. These tuning forks originally were identical, but then we put this extra mass on this side. Is that extra mass going to speed things up or slow things down? Slow things down, yeah. And that's important because in one of your homework problems, we put a piece of clay on one of the tuning forks. And people are always asking me, well, did that make the frequency go higher or go lower? Well, is it moving faster or slower? Slower, okay? So now, this one is going to be a little bit lower frequency than this one. And I'm going to sound them at the same time. Do you hear the wah-wahs? Okay. Now, the reason for the wah-wahs is superposition. If I've got these two tuning forks that started out at 440 hertz, but I put a little bit of clay there to make this one 438, the sound is moving out from those tuning forks at the same speed for both tuning forks, 343 meters per second, speed of sound. But the wave equation says that if the frequency is different, the wavelength has to be different, because it's the product of the two that gives me the 343, okay? And so that means the distance between the compressions on this one, these are going to be further apart than for this tuning fork. Now, as this propagates, what that means is that sometimes you're going to get regions where I've got compressions from both of those tuning forks reaching your ear. And that's when it'll be loud. And then you'll have other times when you've got a compression from one tuning fork and a rarefication from the other, and that's where they'll cancel out. And that's what gives you the wah-wah, okay? Now, I've got a little representation of that. That green dot represents a little particle that is being pushed on by two different waves, the red one and the blue one. Those two waves have slightly different wavelengths because they have slightly different frequencies. And I want you to watch the motion of that little green dot, that particle, as they go past. So, what you see is that sometimes we're adding the pulses and getting a much bigger push on the particle, and sometimes they're canceling. What we find is that if we have two frequencies, one that's 10 hertz and one that's 12 hertz, what we'll get is places where I've got a crest meeting a crest, and I get a supercrest. And here I've got a crest meeting a trough. Oh, I'm sorry, I spoke wrong. That's a trough meeting a trough, giving me super trough. This is a crest meeting a trough, giving me 0. Hold on. And then I get a trough meeting a trough, a super trough. And what we get is a wah, wah. Okay? Wah, wah. Now, it's not an accident that I get two wahs in the same time that I had a difference of 12 minus 10. So the difference in the frequency is going to be the frequency of the wahs.
What determines the
What's that?
What determines the direction of the trough?
The direction of the...
Trough, like whether it's going up or down. Like what is the?
It's an up is a compression and a down is a rarefaction where I've got lower than atmospheric pressure.
With respect to like the air that's
On your
inside.
ear, yeah. So when we have two different sources, the beat frequency will be the absolute value of the difference, okay? And that's how a piano tuner can tell whether the piano's in tune. He takes a tuning fork that's 440 hertz. If that string on the piano is supposed to be 440 hertz, he sounds both of them. If he hears wah-wahs, he tightens or loosens that string until the wah-wahs go away. Okay? Wah-wah is a technical term. Now, I've tried to duplicate this demo here, but I've not been successful. So I'm just going to show you a video.
Now, those of you that go to church, you know that the organ makes high frequency noises and low frequency noises, the noises we call music. And it's the long pipes that make the low notes. Well, I've got two organ pipes here that are slightly different length, and so that means they're going to make, through a process we'll understand on Monday when we talk about longitudinal standing waves, it's going to make two slightly different frequencies. And I'm going to sound them both at the same time, and you should hear beats. Now, I want you to appreciate something. Just for a moment, think about all the old fat professors that have had their lips around that in the last 40 years. Okay, there's nothing I won't do for you people. I love you, okay? Okay, you heard the wah-wahs? Okay, now, if you can do a demo with fire, why wouldn't you? Okay. Now these Bunsen burners are there just to make white noise, to make frequencies at all different frequencies, to sputter. If I had a different way of making a sputtering sound, I probably wouldn't. I'd probably still use the flame. That source of white noise creates all these different frequencies, and we're going to find on Monday that there's one frequency that wants to resonate with this tube, this length of tube. It's this frequency. Okay? Now we're going to find on Monday that that frequency that resonates, that makes the loud booming sound, is determined by the length of the tube. So if I have another tube that is slightly different length, it's going to make a slightly different frequency. And so if I sound them together,